So this week I've decided to do things slightly differently in the sense that so this week's material is about LDA and topic modeling. So the previous year's exercises and all those were relatively simple and like direct questions from whatever you have in the slides. So I found that discussing that won't be too much useful. You can go over them on your own pretty much. So instead, this week I'm deciding to show you how these things actually work by taking a practical example. So, in today's discussion, you can think that so I have this IPython notebook which I've opened with Google Colab, and this has the very rudimentary or very simple approach to LDA, like the most simplistic way you can perform LDA on any corpus or any kind of data set that you have. Okay. So the idea is that in this notebook, there are some portions which are left as blank, and we will solve those, and we will also see how LDA works, what is its usefulness, so on, through this example, so to say. Now, if any of you have knowledge about these different packages like sklearn, so we will be mostly be using scikit-learn today. So if you have any idea about scikit-learn, that is well and good. But even if you don't have, that won't be too much of a problem, because we'll just be accessing some common functions which you can directly invoke. All we need to know are what are the inputs and outputs, what are the parameters, that's all. So it's not something too complicated. Meanwhile, we'll also have a look at some other aspects about running codes like this. Okay, so let us begin. So first of all, a short introduction about topic modeling. So the idea is that this is an unsupervised method. So as you know, in machine learning there can be supervised or unsupervised methods. So in supervised methods we have a gold standard decision or like a supervision. So we know what is actually true and what is not. But unsupervised means that it needs to extract whatever it can from the input itself. There is no guidance given to the model as to like what are the gold standard levels and so on. So there is no supervised training involved. Whatever the model has to learn, it has to learn directly from the text. It does not have access to any other kind of information. So as you know, like topics basically refer to themes or like some kind of ideas that capture whatever is being discussed in a document and so on. So these unsupervised algorithms, what they do is that they extract features from words in documents, and then they use different mathematical operations to divide the documents into different topics and so on. Okay, so each document can consist of several topics, and each topic is connected to a particular group of words, and those words represent the possibility that such and such topic is relevant and so on. And depending on what kind of words a document contains, the topic of the document will be reflected accordingly. Okay, so let's look at what we need to do. So about the material, so definitely after the discussion I will not just update like not just upload the PDF of this entire document, but I will also put up the IPython notebook. So if you want, you can then run it directly on Colab and tweak or do things on your own. So I will do that, so that's not a problem. So I hope you can see, like, do I need to make the font larger, or can you see more or less the things that are written? Anyone? Like, are these visible, or do I need to increase the font?
It's visible, sir.
Okay, so I guess we can go with this. Otherwise, then it becomes too cumbersome to deal with. So, uh, yeah. So importing necessary packages. So well, there are some things which are not that much important over here. So mainly we will be needing pandas. This is for uh, you know putting things in the tabular format and then printing them and so on. NumPy will be needed because obviously we will need to compute those feature vectors and so on. So NumPy is essential for vector operations and all that. RE is regular expression. So regular expression package will be used only for pre-processing. And NLTK, as you know, that is also text processing package. So some functions of NLTK will also be used. And this matplotlib is only used for plotting, which will be needed in one particular segment when we want to visualize our data and so on. All right. Now here you can see that there is this command nltk.download stop words. So this one is basically, as you know, stop words are like a collection of words in a given language, which do not add much meaning to any sentence, but those words need to be there to complete the sentence or make grammatical sense. For example, articles and prepositions, these often fall under stop words because they do not contribute much to the meaning of the sentence. They are just there to make the sentence grammatically correct. All right. And this one is just about the way the pandas tables will be displayed, so not much important. And same matplotlib inline is used for plotting. So let's not get into all these right now. We'll see how they are being used and so on. So if you run this, it will be fine. Now let us have a look at the data we are going to be using. So this is a very simplistic corpus. So the reason for using this is so that you can actually see and understand how the topics get reflected from the text inside the documents. So as you can see, there are 1 2 3 4 5 6 7. So there are 7 documents. So each document is like there are actually 8, I think. Yeah, yeah, there are 8 documents. So by document here, each sentence is a document, but you can think that when you actually do LDA in real life, you will have a big text for each. Okay, but here we are taking very simple examples so that we can see how LDA works. All right, so let's see how the sentences look like. So as you can see, the first sentence and the second, they're talking about the sky. Then there is this sentence: quick brown fox jumps over the lazy dog. Then king's breakfast has sausages, ham, so and so. I love green eggs, ham, so and so. Then the brown fox, another variation of this sentence itself. Again, talking about sky is blue and beautiful. And then finally, the dog is lazy but brown fox is quick. So you can understand that these different sentences, already you can see that there are some distinct themes to them. For example, there are these sentences which talk about the sky and beautiful and so on. So like they can be related with the topic weather. And then you have the quick brown fox, lazy dog, and that thing, like there are some permutations of that in 3 sentences. Though those sentences can be thought talking about animals. So the topic can be thought to be animals. And then finally we have these 2 examples where they are talking about food, obviously. So you will have a corpus, and these are the gold standard labels. Now, as I said previously, LDA is a unsupervised algorithm. So we don't need the labels per se. But here we are taking the labels to measure the performance of the model and so on. So this is a make-believe data set or like a toy data set. This has been created by someone to demonstrate this example. So both the corpus and the labels are created by us. You can think of that. But in a real setting, you will have a corpus that makes sense and also labels that are truly associated with it. Okay. So the labels are for measuring the performance of the LDA model and so on. The LDA model itself does not need the label information to find out the topics because it is an unsupervised algorithm. Okay, so as you can see, this is a corpus which is a list of strings. The labels is also a list of strings. Now, as you can see, as I had told you that in the notebook, different places, some portions have been left blanks and we have to fill them up. All right. So the first step, for example, is converting to a NumPy array. So now that is quite straightforward. We just need to use this command np.array of corpus. Now what does this do? So this is a list. np.array command converts this list to a array. Now NumPy arrays are very flexible. You can even store strings in NumPy arrays. Like there are some other kinds of arrays which only support numbers, but NumPy arrays can support all kinds of data type. So this is nothing but just converting the list to a NumPy array. Why did we do this? Because later this NumPy array itself will be needed when we want to construct the data frame. Okay, so now we have to convert this corpus to a pandas data frame. Now as you know, like pandas is one of the most widely used tools in data science because of its flexibility. Now pandas is basically a package which helps you put things in a tabular format, and then you can play around with the table in different ways. Like you can access individual columns, individual rows, you can operate some particular function on all the rows and so on. So pandas is basically making the things convenient for us. Otherwise, theoretically, we could have still operated with lists also. Like that is not a problem, but converting it into pandas will make it easy for us to visualize a lot of things. Okay. So how do we convert a NumPy array to a pandas data frame? Well, that is not too difficult. What we need to do is, so PD, as you know, here we have imported pandas as PD. So PD dot data frame. Okay. Sorry, PD dot data frame. Now, what is this data frame? So a data frame in pandas is basically a 2D array. So the 2D arrays are called data frames. So two-dimensional means that we must have some idea of rows and columns. So in this case, we have two kinds of columns. One is the column for the text of the corpus, and the other is the column for the labels. And we have 8 rows corresponding to the 8 different examples. Alright. So what we do over here is that you just need to specify a dictionary and you need to pass it to pandas. Now what is this particular dictionary? So this dictionary has to list down both the columns, or like whatever columns you have, those have to be listed down in the dictionary. So this is in a column wise format. So here, as I said, there are 2 columns. So one are the documents. So document becomes corpus, and the other column is labels, or we can say category. So this is like the gold standard we have defined ourselves, and we put this over here. Okay, so when we run it, you can see that this is how the data frame looks like. So in pandas, a data frame, as I said, rows and columns. So these are the 2 columns we have, document and category, which we specified explicitly in this fashion, in this line. And on the other hand, these are the indexes, like indices for the rows. So pandas provides us the option of giving any kind of name we want to individual rows and individual columns. So here we have given the names as document and category to the columns. We have not named the rows in any way. Later in this assignment only, we will see one example where we will have to give names to the rows also. Okay, so this is how the thing is looking like. So we have this corpus, we have these text documents, and these are the categories. Okay, now before any kind of NLP application, we need to do pre-processing. So what is pre-processing? It depends on what particular type of operation you want to do. Like modern deep learning based approaches require very little pre-processing. But when we are talking about these kind of models, standard machine learning models, they depend a lot on how well you pre-process the data. So in this current example, we will only consider these operations for pre-processing, which is we will remove all symbols and punctuations. We will make everything into lowercase, and then we will remove unnecessary white spaces. And finally, we talked about stop words. So stop words often impact the distribution of a document. So we don't need those stop words because they don't make much sense, especially if you are thinking of doing LDA. We don't need the stop words. They don't convey any sense as to which topic it might belong to. So we will have to remove them. Now, definitely these are not the only steps. There are a lot more that could be done. You can try them out on your own if you wish. So you can do other things like removing hyphens, lemmatizing, then stemming, and then removing short word tokens, then removing some rare words or unknown words which are not found in standard dictionaries and so on. So these are things you can try, but for simple pre-processing, these few steps are sufficient. Alright, so again we come to this block of code, and as you can see here, there are two things defined. One is this WPT. So this is the word punct tokenizer. So what this does is basically it divides or tokenizes a text and the punctuations. So it splits apart all the words and the punctuations from a given sentence. And this is like under the NLTK package. So we are directly using the NLTK library for tokenizing. And previously, if you remember, we had downloaded the English stop words. So here we get that list. So there basically the thing is that NLTK has some external resources which do not get installed when you install NLTK. So for example, these stop words is an external resource for NLTK. So if you did not do that previous line of nltk.download stop words, and you just put in this line over here, stop words equal to nltk.corpus.stopwords.words English, then what will happen is that it will throw an error and ask you to download the stop words. So pretty self-intuitive. We have done it previously, so we don't have to worry about that anymore. Otherwise, you will have to do nltk.download stop words over here if you have not done it previously. Alright. Now let's see what we have to do. So here it said normalize document, and a document is passed. So in our case, a document is a string. So a string is passed to this function, and this function is responsible for doing all the pre-processing. And these are the different steps which have been marked out. So lowercase and remove special characters or white spaces, then tokenize the document, then filter stop words, and then recreate the document from filtered tokens. So these are the 4 steps which we have to do. Now, as you know, in Python, there are often multiple ways of executing the same piece of code. So you can write a big code for that, 10 lines, 15 lines, or you can write a more complex code but which is a one-liner. So as you know, Python has many of these shortcuts and tricks to get things done quickly. So yeah, like there is no one standard way of doing these things. You can do it in any way you want as long as it works. Okay, so let's see what we have to do over here. So the first is we have to do lowercase, and then we have to remove the special characters and white spaces. So let's think about removing special characters and white spaces. How do we do this? Well, we can use the regular expression package. So what we do is, so there is this command re.sub. What this re.sub does is it replaces the pattern. So you have to first specify a pattern, and then you have to pass an input string. So the re package, it will look into the input string, and look for that pattern, and wherever it can find that pattern, it will replace it with the output string that you specify in this function itself. So basically this function, as you can see, the signature of the function is being shown over here. So you have to pass the pattern, and then you have to pass the replacement string and the original string, and then there are a lot of different parameters which can be used. So let's see which ones we need over here. So first of all, we have to describe the pattern, right? So as you know, a regular expression is defined like this: r followed by whatever the pattern is inside single quotes. So this is our pattern. We will replace the pattern with nothing, means basically we want to find out the special characters and so on which we want to remove, and thus we will replace those patterns with nothing, so they get removed, right? The original string is doc, and then there are some parameters, but we'll look at that in a moment. So let's first try to find out what will be the regular expression over here. So what do we want to do? We want to keep only the alphabets. Okay, we want to keep just the alphabets and like standard white spaces. Everything else, symbols, punctuations, all those things, get rid of them. How do we get rid of that? Well, firstly we need to do this, which is what does this mean? So this actually, small a to small z defines the range of letters. Capital A to capital Z is also a range of letters. So and this caret before signifies not. So anything which is not falling in small a to z and not falling in capital A to Z, and also not a standard white space. So these are the three type of things we will keep. Everything else will be removed. So anything which is not inside small a to small z, not inside capital A to capital Z, and not a standard white space like space and tab, those will be removed. Okay. So as you can see, this is the pattern. Wherever this pattern is found, we will remove them, which is substituting it with an empty string. So this is the substitution command. There are some other commands inside the RE package as well. And we pass the document, and here we pass two parameters. So these are called flags. Now what are these? Basically these kind of have some kind of other information which the RE package will use while it is trying to find the pattern. So what are these things exactly? Well, so this is the RE library documentation. So as you can see, they have a section called flags. So for example, re.I means ignore case. So the pattern will be matched irrespective of the case, which is like irrespective whether the document is in uppercase or lowercase. Fine. So re.I is simple, and re.A is saying that it will only do ASCII matching instead of Unicode matching. So this is needed for, because there might be some characters and things which are not part of the ASCII code and so on, but we want to do only ASCII matching. So that is why we have given these two flags over here. Now this command will work very well even if you don't pass these flags, but this is just like I'm also introducing you a bit to this idea of flags. So even if this ASCII flag is a bit confusing, this is pretty straightforward. It is saying that you ignore what the case is, and if it matches, just match directly. Alright. Now what we do is we also have to do lowercase. So this is straightforward. The lower command will convert everything to lowercase, and then we also need to do this. So does anybody know what this function is, strip? Have any of you ever used this function? So strip, basically what it does is, if there is any, if you have a string and there are leading or trailing blank spaces, So by leading and trailing blank spaces, I mean like there is some extra space in the front and then the letters are starting, or if there is some extra space at the end. So all those will be removed. Like only at the beginning and end. The strip command is only for removing extra spaces at beginning and end. It won't touch anything inside the main text part. Alright. Then we have to do tokenization. So that is straightforward as well. We have defined the tokenizer over here. So we can just say something like this, which is so this WPT object, it has a function tokenize which splits the thing into list of tokens. Now they are saying we have to filter the stop words. So there can be one way of doing so. This is a list of tokens. Among this list are some tokens which are part of the stop words. So they have to be removed. So one way is you run a loop, you run a for loop, and for every element of this list, you check whether it is belonging to the stop words set or not. And if it is not belonging, then you add it to a new list, and then the new list will contain only those tokens which are not part of stop words. That you can write very well, but here I will show you how to do it in one line. Those of you who are familiar with Python will know this format. So filter tokens. So this is known as list comprehension. So you build a list by defining how the list is, how the different elements will get combined. So this is a one line command, and the way we do it is, so here we have defined stop words, and here we are saying build this list from the tokens list if any element is not in stop words. So this automatically filters out all those tokens which are part of stop words. Now this particular piece of code can be written in many different ways, as I said. So this is one of the simplest ways to do it. And finally we'll have to create the document back. So now we have a list of tokens. We have to again get the document back, which is the string, and the tokens will be separated by space. Why? Because the functions after this will require that. Okay, so what we do, we just say doc equal to, now we want to join all the tokens with white space. Again you can run a loop, then keep adding white space and the new token to a existing string, and then you will get the final string. But again we'll go for a one liner. So this join command actually takes a list and joins the entire list using whatever string you have before as the demarcator. Okay, so basically if you have three tokens, say A, B, C, then this will give A space B space C. So exactly what we need. So this function is then done, and then this is something they have already given. So that is basically passing this function onto another function, which is np.vectorize. This is a standard function. So you convert, so this is a string, the string gets converted to a vector using this. So how does all this work? Let's see. So I run the function. Now I have to normalize the corpus by calling this function on the existing corpus. So I have corpus df over here, which is my existing corpus, and I want to normalize that. How do we do that? Well, pretty straightforward. We have defined this function over here, which is a wrapper on the normalize document function. So we just call normalize corpus with, we are not touching the corpus df because that is needed for visualization. We will instead work on this np array, which is the actual corpus. Can you see the output? Can you see how it has become shortened? So for example, the first thing was the sky is blue and beautiful. That has become sky blue beautiful. So the is, all those kinds of words get removed and everything has become lowercase. You can see that. Then the next one, I love a beautiful sky or something, it was like that. So that becomes love blue beautiful sky. So everything gets normalized. Then this kings, this had an apostrophe s, the apostrophe is gone, and so on. So as you can see, this is the pre-processed data. Okay, and this norm corpus will be the input for our next step, which is vectorization. All right, so pretty straightforward so far. These are like simple pre-processing steps which you will need to do for any kind of NLP application. Now let us look into vectorizer. So as you know, there are these terms which are like turn frequency. So the turn frequency indicates how many times a particular word occurs in a particular document. Okay, so every document, so if you suppose you have a corpus and you decide a vocabulary, so you say that, say these 10 words are my vocabulary, then every document in the corpus can be represented by a vector of length 10 if the vocabulary size is 10, and that vector will contain the number of times the corresponding word occurred in that document. So this is a simple like bag of words vector which just counts how many tokens are there in a given document. All right. So again, you can write codes to calculate that. We have this corpus. You then write a code which will go over the entire corpus and count which word occurs in which document, how many times, and all that. But we don't need to do all that raw coding because we have Python packages available which help us. So here we use the count vectorizer function or the count vectorizer class from sklearn. Okay, so what this does is basically you pass the corpus and it will do things automatically. How does it do that? Well, firstly we have to initialize the count vectorizer. So that works in this way. So we call the count vectorizer, and there are a lot of things which you can pass, but we will have a look at what actually is needed. So as you can see here, I've opened up the documentation for count vectorizer and there all the parameters are given. So as you can see, you have to pass the input either as a file name or a file or a content. So here we will pass content, and the content input is expected to be a sequence of items that can be type string or byte. Can you see this last part? So over here we have already converted the corpus into a format where every item is a string. So then we can directly use the count vectorizer. Okay. So as you can see, the default is content. So we don't need to pass this argument per se because the default value is content. We need to just look at two things over here. There are a lot of other parameters which might not be very important right now. Just look at two things, min_df and max_df. So these are like these are cutoffs or thresholds as to for building the vocabulary, which term should we consider. So as you know, if some word occurs very less in one or two documents, it's probably not that important. Similarly, if a word occurs in every document, then it is most likely to be a kind of stop word. So then also it loses its value. So that is why these values can be specified explicitly as to whether you want to cut off some words from the vocabulary and so on. But in this case, we won't do anything. What we will basically do is we will just set the min_df to 0 and the max_df to 1. Okay. This is the only thing we will do over here. So min_df becomes 0.0 or 0 point. You can write it like that also in Python. Max_df equal to 1 point. Okay. So we have initialized the count vectorizer and now we need to feed the vectorizer to our data, or in other words, we need to run our data through this function so that all the documents get converted into vectors. How do we do that? Well, if you can look at the documentation later, but there is this function called fit transform, and we just pass the normalized corpus directly, and that gives us a matrix. As I said, it returns a vector for each document, and you have certain number of documents. Here we have 8, so then it becomes a matrix, right? 8 cross number of terms in the vocabulary, that becomes the matrix. So count vectorizer actually returns a matrix for a corpus. Let's see how it looks. As you can see, it is saying, so the idea is that these store things internally in a different format, which is a sparse matrix. So the values explicitly won't get printed if you just try to see what the variable looks like, but you can see its dimensions. So 8 cross 20, 8 rows and 20 columns, so that means the vocabulary size is 20. Okay, fine. Now this is, as I said, this is the sparse representation. If we want to actually visualize, we have to get the dense representation. So you don't need to understand exactly what are the difference between that right now, but the idea is, as you can understand, when we do bag of words and there is a large vocabulary, then for every document there will be many words which will be 0, right? So if you consider the overall matrix, there will be a lot of zeros. To save space, this is another format of saving things so that the space is saved, which is the sparse matrix format. But that is not ideal for visualizing it, because you won't be able to see it in that tabular way, rows and columns kind of thing. So when we want to do that, we use this function .toArray. Let's see how it works. So this becomes the matrix, as I was saying. So this, each individual row is the vector representation for each individual document. And like if you okay, so in the let's see which column corresponds to which word, then you will get it more clearly. So here we are just these are some more functions, and we can put the names of the words in the vocabulary as the columns. So that is what it actually is. So if there are 20 elements in the vocab, these 20 values signify whether those words are present in what number. So here you can understand it more explicitly. So these are our documents numbered from 0 to 7, and these are all the words. Okay, these are all the words in the vocabulary. Like, it's not fitting completely here, like there are more, but this comprises of all the unique words, and then we represent each document in terms of that. So this is pretty straightforward, and we get this this is the vector format for every document. Now this is the last step we need before performing LDA. Okay, now let's see a bit about LDA. So this latent Dirichlet allocation, that actually learns the relationship between words, topics and documents. So you have words and you have documents given to you. Now there are these topics which you need to find out, and these topics are related inherently with words and documents. Okay, so like some presence or absence of particular words will indicate whether a given topic is applicable or not, right? And a document is a collection of words, so the topic of a document will be determined by the type of words it contains. Formally speaking, topic in LDA is a multinomial distribution. Given a topic, it's more likely to see specific sets of words. Okay, so what does LDA give us? So LDA gives us which words are more likely to be connected to specific topics. So this is a topic by word matrix, relation between topics and words, and which topics are more likely to be connected to specific documents. So document and topic relation. So one relationship between topics and words. So each word can represent multiple topics, and each document can have multiple topics with different probabilities, obviously. And to interpret a topic in LDA, for each document you can think that all the topics have some probability. So if we take the top n, then those are like the possible topics for a given document. Okay, so without going too much into all this, let's see how it works. Okay, building the LDA model. Well, we will use the count vectorizer output directly. So here they mention we should not be using TF-IDF vectorizer because LDA does the TF-IDF weighting itself. So it actually needs the raw count of how many words occur in how many documents. Okay. So with all that done, let's see how to do this. So first you have to define the LDA model. So again, this we import this package Latent Dirichlet Allocation from sklearn, and we have to define the LDA model. So we follow the standard thing, which is sorry, which is we do this. We call this latent. So now you can see in, as you know, in Google Colab, they give you this highlight of what are the possible, like what are the function parameters and arguments and so on. So here we won't be needing all these things. As you can see, there are a lot of hyperparameters and so on. We don't need all of them. We just need a few, which is the number of components. So this is one parameter you have to provide to LDA, that you have to tell how many topics are possible, because it does not have any idea. If you tell it how many topics are there, then it will divide the words and documents in that sense into those many topics, because the model itself has no idea about what are topics. So you need to say that among my corpus, 3 different topics are possible, and then it will try to distribute everything accordingly. All right. So this is a hyperparameter which we can choose. In our case, we know it's 3, so we are passing with 3, but ideally this is also a hyperparameter that has to be chosen when you do the experiments. So we pass 3. Okay, so let me write it out, then it will be easier. So n components is 3. Then we have max iteration. So this is a machine learning algorithm which will run multiple iterations over the data. So we specify that. So here I am doing 10,000. And then there is this thing which is called a random state. You may choose not to use this also. So this basically this makes the LDA, like there are different parameters which can be non-deterministic, but when you set a specific value, then it becomes deterministic. So that's all you need to understand for right now. Even if you leave it out, it's not a big deal. The main thing is this parameter, number of components. This has to be provided. And max iterations obviously depends on your system and resources and so on. So here we have defined LDA, we have defined the LDA model. Now we need to fit it to our data, just like we did with the count vectorizer. So how do we do that? Again, this also has a fit transform method. We call the fit transform method with the normalized corpus. Sorry, not the normalized corpus. We got this as an output of, can you see this one? We got a CV matrix, right? The CV matrix is the output of the count vectorizer. So we have to pass that one directly. So we pass CV matrix. Okay. This is
Excuse me, sir.
Yeah.
Can you please tell me that why max iteration you have taken 1,000? What is that?
So basically what it does is like it runs multiple passes over the data. So like the corpus we have, the model will do many iterations over the data to find out what are the possible topics. So it makes some assumption and it tests it out on the data, and then it makes some changes and then again runs it on the data. So you have to run it multiple times, then the model will converge. So if you have an idea about standard machine learning algorithms, they also work on iterations. So it passes over the entire data multiple times and keeps improving its parameters on every run. And ideally, after a point of time, you get saturated. So this is like a hyperparameter. Hyperparameter means this is a value which you have to tweak and see which gives you results and so on. So there is some default value of this function, obviously. So if we look over here, this is the LDA documentation. So by default the max iteration is 10. Okay, so this is given. By default it will run over the data 10 times. But actually we need a lot more iterations, and it is pretty fast also, so that's not a problem. So that the model converges. So I have randomly chosen 10,000 over here. You can very well choose 1,000. You can choose 100 also. So that does not matter very much over here. It's more about you try different values and see which gives you better results in the end. This is how this is how we tune hyperparameters in machine learning. Okay, this.
Okay, got it, sir. But I have one more question.
Hmm,
Actually, it's very silly because I'm hearing this term so many times when the model converges, right?
hmm.
So what does that mean? Converges means exactly what's happening.
Okay. So let me explain in a very crude way. Then, in a very simple example. So suppose you are learning a new mathematical formula. Okay. So the first time you learnt it and you applied it on a given problem. Maybe it came wrong. You forgot some part of the formula. Okay. Then you will again go and have a look at the formula. Then the second time when you use the formula, more likely that you will get it correct. Second time also you can make some mistake. Then you will again look and then again do. So this is what we mean by multiple passes. And when you are doing this after a point of time, say after 5 times, after 5 times the formula is already by heart to you. Like you know the formula by heart. You don't need to see it again. You will get it accurate. Okay. So that means your learning has converged. Doesn't matter when it is converging. That means even if we keep on repeating, the performance does not change. That is what we mean by converging.
Okay, got it, got it. Thank you, sir.
Okay. So as I was saying, these are all hyperparameters. The most important hyperparameter is this one, the number of components. Here we are taking a toy data and we know there are roughly 3 kind of topics. That is why we are specifying 3. But ideally this is also a hyperparameter that should be checked out with different values. Okay, to see which gives the best possible understanding. But because I'm just showing you how to write how these codes work, that is why for now we are going with just 3. And we pass this. Okay, let's see what happens. So as you can see, this will take slightly bit of time because we are doing a lot of iterations, and yeah, it's done. So this command over here on top, percent time, that actually measures the time taken by the block of code inside here. And as you can see, it is printing the different times which it's calculating. So more or less 8 seconds. Within 8 seconds this is done. So you can understand with 10,000 it is 8 seconds. If you make this say 1 lakh, then it may take close to 80 seconds. Roughly, like not guaranteed, roughly. Same way if you take lesser, it will run instantly and so on. But anyway, this is now trained, and this is the output doc topic matrix. So this is a relationship between the 3 topics and all 8 documents. As you can see, it is showing an ND array with shape 8,3. So basically it is giving some kind of scores to the 3 topics for each document. So for document 1, topic 1 some score, topic 2 some score, topic 3 some score. And obviously the topic with the highest score is more related with that document. Alright, let's try to understand this. But before that, there are these 2 metrics which are like standard for reporting the values of a LDA model. So one is the log likelihood. So both of these you can get directly from the model's output. So this is basically the trained LDA has a function called score, and we pass the CV matrix to it, then it will give the log likelihood. Similarly, we can pass LDA dot perplexity for calculating the perplexity. We just pass the CV matrix. So these are like defined functions. If you look at the documentation of LDA, you will find that. So we get some values. Not very important to us right now because we are not comparing multiple models. When you compare multiple models, then you will see different values of perplexity, and The lower the value of perplexity means the model has learned better. Okay. Now is we have to understand what, like, we got this, as I said, this doc topic matrix is a 8 cross 3 matrix. So 8 cross 3 ND array. So what does this mean? We have to get some kind of interpretation, right? So let's see, how do you interpret the results? So, for example, as I said, the labels we knew. There were three labels: food, animals, and weather. But suppose we don't know what are the labels. So we just have T1, T2, and T3 for representation purposes only. So this is how this thing looks. How that, like, the output of LDA looks. So for each of the three topics and each of the 8 documents, you have a score. So for example, document 0 has a very high score with T1 and very low with T2 and T3. 0.83 with T1, 0.08 and 0.08 with these two. Okay. And obviously you can understand that these will sum up to 1. Okay. Like, these are probability distributions, so they will sum up to 1. So 0.83 plus 0.083 plus 0.084 will give you 1. So basically it's the probability distribution of topics over documents. Alright. Now we need to get the relationship with the words. Then only we will understand what each topic is capturing. Okay. So there is this topic word matrix, and we need to find this out, that how each topic is related to each of the words. Here we have each topic related with each of the documents, but we also have to find out how each topic is related with each of the words, because we are just saying T1, T2, T3. What is T1? What is T2? We don't have any idea, right? So we just know they are 3 different topics, but what are they exactly? To get that, we need to find out which words correspond to which topics. Then we will have an idea. Okay, so T1 is a topic which is related to words like the weather. T2 is a topic which is related to words like fox and dog and so on. T3 is related with bacon, eggs and ham and all that. So we need to get that idea. So for doing that, we need to find out the relation between topics and words. Okay, so we need to find out this topic word matrix, and that we do in this way. So again, there is something called LDA dot components. Okay, so LDA dot components, there is a hyphen at the end. As you can see, this actually represents the topics, relationship of the topics with the different words in the vocabulary. If you read the documentation, you will get that. So let's see what it looks like. Okay, we ran that. Let's visualize it. Okay, so now you can see we have all the 20 words in the vocabulary, and we have the 3 topics, and then again we have some kind of scores. These are not probabilities, these are scores. Okay, this is difficult to visualize, so we just transpose the inner matrix for visualization. So in this assignment, everywhere we have used pd.data frame is only for the purpose of visualization. If you skip the pandas part, you can very well do the entire thing with just numpy arrays. But this is for understanding the relationship. So okay, these are the 3 topics, 0, 1 and 2, and these are each of the words. So we can see the word bacon has very little relation with topic 0 and topic 2, but very strongly related with topic 1. Beans is also strongly related with topic 1. Beautiful is strongly related with 0. Blue is also with 0. Some kind of relation with 2, and so on. You can see that breakfast, strong relation with topic 1. So already we are getting an idea that topic 1 probably has something to do with food. If you look at all the food items, eggs, ham, all these things have very high score in topic 1 and low scores for the others. Similarly, if you look at things like dog, fox, they all have very high score in topic 2 and low for the others. So we are already getting an idea what each of the topics actually represent by the meaning they carry with each of the words. So this is the basic idea. Because this is unsupervised, You can think in real world you might not have the gold standard labels, and the model will just say there are three topics. But what are each topic? To understand that, we need to find out the relation with the words. Then only we can get an idea of what each topic possibly represents. And then you will have some ambiguous cases like love. You see, love is 1.33 with topic 1, 1.33 with topic 2. Okay, so there will be some cases like that. But there will be some words which will strongly correlate it with one particular topic and not with others. Okay, so okay, this is done. Now let's see this. So this is a function which has been defined, and the LDA does not give us a label for each topic. It is the analyst who determines the meanings of topics, as I said, and the decisions are based on words under each topic. So now what we want to do is, under each topic we want to find out which are the important words, or which are the words that have high scores. So we can get an idea by looking at the table, but we want to find it out in a more formalized way. So what do? We represent each topic as a ranked list of words. Ranked list as in the word having the most correlation with that topic will be the first, then the second word, then the third one, and so on. Now this function, the way it has been defined is, it can work in two ways. Either it can display, like you give a weight cutoff, and all the words that have weight higher than this will only be printed for a given topic. Or you can specify top n, which is the top so many number of uh, words per topic that you want to see. Now it might get a bit confusing, so let's just finish this one quickly so we can understand what is all happening over here. So the topic word matrix has to be passed over here, the vocabulary also has to be passed, and these are like other parameters. So we take each row in the topic row matrix, and for all words, so we take this tuple where this is a word and this is its weight, rounded off to 2 decimal places. So we take this tuple of word comma weight, and we find out that list of words and weights for each topic. Okay, so that is done over here. Now we will have to rearrange this list so that it is sorted. The words having the highest weight should come at the front, and vice versa. How do we do that? Well, that is also pretty straightforward. What we do over here is, we do, so you know there is this sorted command which you can use for sorting directly. And how will we sort? So each element in this list topic is a tuple. How does the tuple look? Well, the first element is the word and the second element is the weight. So when we sort, we will sort on the basis of the weights, right? So you need to remember this, and you need to specify that we will be sorting on the basis of the weights, and we want it in descending order. That is why reverse equal to true. Okay, if you don't give this part, it will come in ascending order. We don't want that. We want the highest words to come front. Okay, and as you can see, these parts are already coded, not for us to fill in. So they are making those understanding, like if the weight is greater than cutoff, then only it will be printed, and so on. Here also only the top n words are being chosen, and so on. So this was already given, only this part we had to fill up. So let's see how this works. Okay, so here we have to actually call that function, display words having weight higher than 2.0 per topic. So for every topic, only the words having weight more than 2 should be printed. How do we do that? Well, we just call the function get topics meanings, and we call it with, firstly the first parameter is the topic word matrix, the second is the vocab, then the other parameters we have to set. How do we set that? Well, display weights is true, we want to see the weights, and weight cutoff 2.0 they have already mentioned, so we pass this. Can you see the output? This is where it starts to make sense. So for topic 0, the most probable words, or the words with the most weight, are sky, blue and beautiful. For topic 1, the words having weight more than 2 are bacon, eggs, ham and sausages. And for topic 2, it is brown, dog, fox, lazy and quick. So here, when we do this analysis, so this is a function is which is not provided by sklearn or anything. This function had to be coded, right? Why did we code this function? So that we can visualize things in this way. So this is a part of this assignment, but it's more like when you have to visualize things, then you have to do these kind of functions, write them up and so on. Otherwise, this is the output of LDA, and by visualizing that we get an idea of which word corresponds to what. But to get it more formally, we did this. So you can see this is how it's coming. And then the next one is display top 3 words under each topic. So again we will call the same function, get topics meanings, topic word matrix, vocab. We don't want the weights to be displayed, so display weights equal to false, and top n is 3 words under each topic. So you can see these two things are correlated. It's just the way we are filtering out the lists. So sky blue beautiful, bacon eggs ham and brown dog fox. Okay. Now like we are more or less done with the LDA thing. Here we will just have a look at how the LDA models outputs correspond to the real values. Okay. So we know these are the actual topics: weather, food and animals. We do this. Okay. So doc topic DF was the output of this, right? Sorry. Doc topic DF. We got doc topic DF from here. Doc topic DF. This thing was there. You can remember. So now we now know what T1, T2 and T3 are. That is what we got from this analysis, right? So we know T1, T2, T3. So now we are giving the actual names, and we are also arranging the corpus alongside. So here we get the full thing. So this is the corpus, the input, and these are the outputs of the LDA model corresponding to the 3 topics. Okay, we got this.
Excuse me, sir.
Yeah.
Sir, here initially we have decided on 3 topics, right?
Yes, this is just for showing you the correlation, but that decision may not be there. So you may not know what are the actual topics.
Yeah, so on real data set, we don't know how many topics will be there, right?
Yes, we don't know that.
At that time we have to assume number of topics.
Yes, so that part is a hyperparameter. You will have to experiment with different values. As I said, here is that hyperparameter, n components. So in LDA, we are specifying how many topics will be there. Here we know it is 3, but when we don't know real world data, then we'll have to experiment with multiple values and see what is making more sense, which has the lowest perplexity and so on. So you'll have to do 2-3 different studies to actually understand what will be the best value for number of topics. Okay.
And the next question is, here you have specified the labels, weather,
Yeah,
food.
yeah. That is just for correlating with the toy input that we have. But, ideally, you won't be able to do this. In real life, you won't be able to do this unless you know what it is. Yeah.
Okay, so ultimate goal is to find that label, right?
Ultimate goal is to find the label, but the label will also be determined by you yourself. I am calling it weather. Somebody can call this sky, because more statements are about sky, right?
Okay.
Then
So
I have called it food. Somebody can call it specifically breakfast, because most of the items are breakfast items, bacon, eggs and all that. Okay.
So So it depends on how you are interpreting the results.
Yes, so this is the part which is qualitative. The model won't be able to quantify that. The model can just say what is the distribution of multiple topics over the documents. Like these are the
Right.
values given by the model. All these labels are given by us, and I have given them here for visualization purpose. You will see in the next block. So I could have very well left it at T1, T2, T3. That was not a problem. So this is not essential for the code per se. This is only for our visualization. As in, we know that there are three topics and we are trying out a LDA model to see how well it understands that. But in real life, you won't have the topics and you will be using an LDA to find them out. Right? So.
Okay, thank you, sir.
Hmm. Then this is plotting. Not going too much into the details of this. You can look up matplotlib later, but this is just for visualizing again. So this is known as a stack plot, and this plot actually tries to map the possibility. Like as you know, every document has a probability distribution over the topics, like with what probability each topic occurs. So here we are just visualizing that. So for example, dog 0 has a high probability of weather, low probability of food and animals. Dog 2 on the other hand, very low probability of weather, very low probability of food, very high probability of animals and so on. So this is just a representation for seeing all that. So I just wrote it so that if you want, you can also use this kind of visualization later on. Nothing to do with actual coding. Uh, then quickly let's have a look at this. So what like we can also cluster documents using the features of the topic models. Okay, so like clustering, clustering is also a machine learning algorithm, unsupervised. It tries to given a group of items, it tries to divide them into different clusters. The goal is that all elements in a cluster should be very closely related and they should be less related with elements outside the cluster. So that is how you find out that cluster. Okay, so just giving a short code snippet so that you can also get an idea about clustering. So what we basically do over here is that we have to use the k-means classifier. So we have already imported k-means over here, you can see that, and we do k-means. Again, k-means has this hyperparameter n clusters. This is again something you have to specify. We know it is 3, that is why we are doing. Random state, again 0, not needed that much. Also this is the main parameter. Okay, and what we do is we do again km dot fit transform on the. So what are we doing over here? The LDA model has returned us a probability of each topic for each document, right? So we are passing those probabilities into the k-means clustering algorithm so that it divides the documents in different clusters. So all the 8 documents we have, so far we have already only talked from the topic point of view, but here all the 8 documents, those documents will also can have clusters, right? Like some documents are talking majorly about food, some are talking more about the sky. So we want to separate them out, and that is why we are doing clustering. So we can take the output of LDA for doing clustering. So this was the output of LDA, the document topic matrix, and that we are passing it into clustering, and we will get the cluster labels also. Let's see what this is happening after all this. So as you can see over here, this category was assigned by us, and the cluster is the output of LDA plus k-means. So we do LDA and then we do k-means to divide the documents into multiple clusters. So here we are saying 3 clusters, or like each cluster can be thought of to be a topic. So we are confirming that yes, indeed, after doing LDA and then clustering, we are seeing that the documents are falling into those respective clusters. So like everything that has to do with weather is getting the level 2 from k-means. Everything that has to do with animals is getting 1, and those that have to do with food are getting 0. So after doing LDA and k-means, we are able to split the documents into 3 different clusters which represent the 3 different topics. Okay. So this is all about visualization and training of LDA. This is the final part. We have a trained LDA model. Now how does it work on new sentences? So we have some new sentences. The sky is so blue. Love burger with ham. These were not there in our original corpus. Now we want to find out which topics they belong to. You know that this is related to weather and this is related with food. Like we can understand by seeing that words. But can our trained LDA model find that out? For doing that, let's do this. What we do is, so new text non, we have to find that out. What we do is we normalize the corpus. So this is a new corpus, you can think, right? This is a new corpus. These 2 sentences. This is not previously seen. So we normalize that. Then we vectorize it. Alright, so you need to know one thing over here. Previously we were using fit transform. Here we are using only transform. Why? Fit transform actually tries to learn from the data, whereas transform is applying the learned algorithm for prediction purpose. So we do this and we get, so 2 cross 20. We know the vocab size is 20 and there are 2 documents, so 2 cross 20. So this is the matrix after the count vectorizer works. So this is that matrix, and then we will get the topics using LDA. So again we do LDA dot transform, not fit transform, only transform. We do LDA dot transform on this. Okay, we do this. Then so like these are just for like visualization again, and here we have to predict the topic. How do we predict? The topic with the highest score will, like, we just print it out as another column, again just for visualizing more effectively. Instead of seeing probability scores over 3 topics, let's just print the topic which the model is predicting to be most likely. How do we do that? Well, uh, that is done in this way. We, so topics I for I in np.argmax. So what does we do? What did we just do over here? Well, this this data frame has the probability distribution. We are doing argmax over that. Argmax means we are taking the argument which maximizes. So basically if there are 3 probability values, this one returns the index which has the highest value. So 0 index there is a value, 1 index there is a value, 2 index there is a value. Argmax returns the index which has the highest value, and that index is I, and then we are putting it into this topics list which has the list of the labels to get the actual prediction. Okay. Okay, something went wrong, just one second. For I, Okay, this is creating some problem. Okay, sorry. Yeah. So by values, we get the values instead of like we get it as a list, and then we take the max of that. So this comes like this. So this is the first document. After normalization, it becomes sky blue. The actual sentence was the sky is so blue. And the next one is love burger with ham. So love burger and ham are there. And we can see these are the outputs of the LDA model. So the LDA model is saying the first one is more related with weather and the second one is more related with food. And by doing this processing, np.argmax and everything, we get the predicted topic. Okay. All right. So that's the end of this. So I hope I could give you an idea as to how LDA works in the real life. Now, obviously, these days people use more powerful algorithms, but if you learn to do these things, these small codings on your own, this will also help you in your confidence for building bigger projects and all. So, yeah, these are the simpler models. You have more complicated models after this, like deep learning models and everything. So, that you can come to slowly. But this will also give you an idea of how to use these packages like sklearn and so on, sklearn, pandas, numpy, because these are very important in data science. And yeah, like I hope I could give you an idea as to how you proceed with the LDA task. Now if you do some other kind of task, there will be some common steps like pre-processing and so on. Um, yeah, so more or less that is this. I hope you don't have any very major doubts. You can have small niggling doubts. I can understand that, but go like once you go over this entire thing on your own once, I hope those will be cleared out. All right, and I will upload not just the PDF for this, but I'll also upload the IPython notebook, so you can use it directly and you can make some changes if you want and see what's changing and all. So that I'm leaving on you. Okay. Uh, all right. So, does anybody have any specific doubts related to whatever I discussed today?
No, sir.
Okay. 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 So then, thank you, and we'll meet in the next class. Okay.
Thank you so much, sir. It was very much informative session. Thank
Yeah, I also thought that let's do this session in a different way because anyway there was not much use in discussing about the theoretical parts about LDA. Like in other weeks we have some theoretical portions which need to be discussed, but this one there was not, so that's why I went with this. So maybe in the next meetings also, if we have similar topics, I'll try to give you practical demonstrations.
you. Right, sir, because practical is very important.
Yes.
So
I also
knowing only theory will not just do.
yes.
So this is very important sessions. So
Yes,
thank
sir.
you so
Yes. Yeah, you're welcome. No problem. Okay. All right.